Hello, welcome to another video in physics. In this video, we're going to be discussing vectors in two dimensions. So the example I'm going to use is a rock climber. We're going to discuss the dynamics of what keeps a rock climber on the wall, seeing as how we're going to be taking a trip to a rock climbing gym. I thought I'd use this as an example. So the rock climber stays on the wall because of the points of contact that the rock climber has on the wall. So the dynamics that are at play are that when a person is climbing a wall, okay, you have a grip and there's a downward force. That downward force is your mass times gravity. So that's the gravitational pull that the earth has on you that's pulling you down. Now conversely, at the same time that you have a downward force pushing you down, there's also an opposing force that the rock is pushing on you. So in fact, in terms of physics, the part that's keeping you on the wall or keeping you up is the wall actually pushing up against you. So you're holding down your mass, your gravitational pull is pulling you down, but the wall has an opposing force pushing you up. Now on top of that, you can see in this example here that this rock climber has a lot of chalk on their hands. This chalk powder is for increased grip. Okay, it actually increases the amount of frictional force that your hand has with the wall, and it increases friction and it actually gives you better grip. So those are the forces that we're talking about, that we're looking at as somebody is climbing a wall. Now as you can see here, this rock climber has, now as far as their body is concerned, they have 3 points of contact with the wall. You see the foot there, and then you see the right foot in contact with the wall. So again, as this person hangs, the gravitational force is pulling them down, but the rock is pushing back up against that, keeping this person up. Now if you pay close attention, you're also going to see the rope that's attached to the rock climber. This particular rope, you can see, is pretty tight. There's not a lot of slack in it, so that means that whoever's belaying him has a tight rope, which means they're actually supporting him. They're helping him stay up on top of that rock because it's pretty tight. Now you'll notice here on this rope that there's a couple of points on the rope where there's some angles. So those angles are points of contact on the rock as well. Those are what we call friction points, points of friction. So his mass is actually being supported not only by his 2 feet and hand, but also by these points of friction. In fact, the smaller the angle of the rope from the point of friction, so if the point of friction is my fulcrum and the rope is my angles, the more narrow the angle of the rope is, the more mass, the more support he's getting. So as you can see from these 3 points of friction, he's getting more support from the point of friction that's closest to him. Now the other one that's on the wall, on these 2 points right here, those 2 points of friction are not supporting him as much as the one that's closest to him. And then of course you have the belayer who's down below, and they actually have another couple of points of friction that are helping him stay on the wall too. Okay, so and then of course you have the force of gravity pushing down on him. So as you can see, a rock climber has many forces working with him, and they're not just your typical forces that we've discussed in previous chapters where there's an up or down force, or even a horizontal force, but these forces are being applied at different angles, more than just the 90-degree angles that we're used to. So several forces are acting on this climber, as we mentioned before. These are multidimensional forces that act in many directions. In previous problems, we've been discussing problems that have forces that are working in only 2 dimensions, a horizontal or a vertical force or direction, and these forces typically make 90-degree angles. So how this video differs from the previous ones is that now we're talking about multidimensional forces, and these forces make angles that are other than 90 degrees. So they're slightly more complicated, and they involve a little bit more complicated math. So these are other than 90 degrees. So these are the two concepts that we're going to be using when we are trying to figure out the different angles that we're working with. So when you have a problem that has something other than a 90-degree angle, these are the two trigonometric laws that we're going to be using. They're called law of cosines and law of sines. Law of cosines, the general equation looks like this. You have r squared, which is typically the longest side. Now, it actually depends, because it doesn't have to be the longest side that's r squared. This is just the parent formula, if you will, of law of cosines. It's r squared equals a squared plus b squared. Now if I stop there, that should look like Pythagorean theorem. Pythagorean theorem works best when you have 90-degree angles, but because we're working with angles other than 90 degrees, we have this additional component to it. We have a squared plus b squared minus 2 times the side of a times the side of b times cosine theta. Okay? And we'll put this into practice in one of our problems coming up. And then you have law of sines, which I will discuss in another video, and that is the r length over sine theta equals side A over sine A equals side B over sine B. And these are ratios, this law of sines. So you use these trigonometric laws under different circumstances. The law of cosines you will use when you're given two vector magnitudes and the angle between the two vectors. And like I said before, we'll work out a problem that has this particular situation. And the law of sines is used when you're given two angle measurements and only one vector. So with cosines, you're given two vectors, and with sines, you're given two angle measurements. So depending on the scenario that you're working with, that will determine which of these trigonometric laws that you're going to. Okay, so I'm going to pause the video at this point, vectors in two dimensions. In order to keep the videos at a reasonable length, I've decided to cut it in half. So this will conclude part 1 of vectors in two dimensions. Watch part 2 to finish and see the rest of this topic.